The idea I'd like to focus on here is rewriting functions into different forms to make them easier to differentiate. In fact, in some of these cases, you won't even be able to find the derivative unless you can write it in a different form. So in this first example, you can see a function. I have a variable exponent. A lot of times we have to write this in log form to be able to take the derivative. You'll notice in this case, it's already written in a log form. So if you remember, when you have a log of a value with an exponent, that exponent can be brought around out in front, and I can rewrite it into that form. And the new form is going to be y equals x times the natural log of x. And at this point, it's just a product rule problem. So I can find y prime by taking the derivative of the first value, 1, times the second, plus the derivative of the second times the first. I do get a little bit of simplification in this case. This is going to end up being y equals the natural log of x plus, notice this is x over x here, which just ends up being 1. So a relatively simple derivative once you write it into a different form. The second example, notice if I have e to a natural log power, e to the x and the natural log of x are inverse functions. So as a result, we can think of those functions as canceling each other out. So if I have e to a log power, that is actually just going to turn into 5x. And of course, the derivative of that, y prime, is just going to be the number 5. So very simple there. Next example, same kind of thing. A natural log of e to a power. Those values are going to cancel. I'm just left with y equals x squared. And of course, we know in this case, y prime is going to equal 2x. Pretty straightforward. Number 4. Again, I can write this in a slightly different form. It looks like a reciprocal inverse, or it looks like a reciprocal derivative. But keep in mind that anytime I have a reciprocal, I can also write it with a negative exponent. I can rewrite this as y equals e to the negative 2x power. And of course, the derivative then of e to a power is going to be that e to that power times the derivative of the inside function, which in this case is going to be negative 2 e to the negative 2x. Or you could write that as negative 2 over e to the positive 2x if you wanted to write it back into the other form. In the fifth example here, once again, I have an exponent that can be multiplied out in front. So I can write that as 5 times the natural log of x. And of course, that's just going to be a constant of 5 times the derivative of the natural log of x, which is 1 over x. So that's 5 times 1 over x, which of course is equal to 5 over x. Continuing to find derivatives with problem number 6, you'll notice here I have a reciprocal function. And the most important thing here is that I should be able to write this with a negative exponent, and this should make it relatively easy. So I'm going to rewrite this as y equals 5x plus 4 to the negative third power. Should just be a power rule problem and a chain rule problem at this point. I have u taken to the negative 3 power, so of course I'll multiply that exponent by the lead coefficient of 1, get negative 3. Inside function does not change. Power drops by 1. And then I need to multiply by the derivative of the inside function, which in this case is 5. And so I end up with y prime equals negative 15 times 5x plus 4 to the negative 4th power. I wanted to rewrite this. I can move 5x plus 4 to the positive 4th power to the denominator of the fraction. Second example here is a log. In general, when you have logs, you can't do something with it, you can change it to another form, and that's what I'm going to do in this case. I'm going to use the change of base formula. Change of base formula says that I can take the log of x divided by the log of 3, or for the sake of having simple derivatives to find, I'm going to take the natural log of x. Answer there. The natural log of x divided by the natural log of 3. And keep in mind, you look at this and you think, this is going to be a quotient rule problem. This is not a quotient rule problem. The natural log of 3 is a constant. It's got a decimal value. which means I can really just think of this as being y equals a constant, 1 over ln of 3, times the natural log of x. And just like if I had 5 times the natural log of x, I could just take the derivative of the natural log of x and multiply it by 5. I could take the derivative of natural log of x here and multiply it by 1 over the ln of 3. So in this case, y prime is going to end up being the constant value, 1 over ln of 3, times the derivative, which is 1 over x, and that's going to be y prime equals 1 over the ln of 3 times x. And actually, I want to write that as x. Ln of 3 would probably make that a little bit less confusing for someone to read. You can also memorize this derivative. It just ends up being 1 over this value times the natural log of the base, if you want to memorize that, or if you just want to do the base change conversion, not very hard to take that derivative either. Okay, the next example, same kind of thing. I'm going to have base change formula, except I'm going to have the base change formula twice. Now, you can write it, that's going to be the log of x divided by the natural log of 4. All of that divided by the same thing, the log of x divided by the natural log of 5. You look at that, fraction looks terrible. However, remember, I'm dividing a fraction by a fraction. Same thing as multiplying by the reciprocal. Take a look at what happens when I multiply by the reciprocal here. I have y equals the natural log of x over the natural log of 4 times the reciprocal is ln of 5 over ln of x. Notice everything's being multiplied here, which means I can divide out a natural log of x from the numerator and the denominator, and I'm left with y equals the natural log of 5 over the natural log of 4. And be careful, it's really easy to look at this and think again that you've got a quotient rule problem here. You don't have a quotient rule problem here. That's a constant. The derivative of a constant is always 0, and I'm done with this problem. Okay? And the final example, really just a big chain rule problem. Notice this is not sine times the tangent of x, that's sine of the tangent of x. So I have an inside function of this, I have a second inside function of that, and it's just going to be a matter of being extremely careful here as I go through the process. So y prime, I have this u cubed, so I follow the power rule here. I'm going to have 3 times that u, which in this case is sine tangent of x. Power drops by 1 down to 2. Now I multiply by the derivative of the inside function. The derivative of that inside function, derivative of sine, is going to be cosine of the same thing. So cosine of tangent of x, strange as that looks. And now I have another inside function. This time I have an inside function of tangent x. The derivative of tangent x is secant squared of x. So I have to multiply by secant squared of x. Could you do some simplification here? Yeah, possibly. For example, I could take, actually not in this case, I was going to say I can turn that into 1 over cosine squared of x, but if you notice, that would be cosine squared of x, whereas this is cosine squared of tangent x. So not any major cancellation here. You basically just get this big, ugly, complicated answer.